In this lecture, we're going to introduce a variety of diagnostics for evaluating classifiers. So far we've introduced things like the mean squared error and R-squared statistic, which have been evaluation techniques for regression models. What are the corresponding set of evaluation techniques for classification models? And secondly, we'll describe different situations where different performance measures may be preferable over others. Okay, so to motivate this problem, consider some classification data like this. We have two classes, in this case stars and peppers, and we might want to select among two potential classifiers. So here are two alternatives. You have classifier A and we have classifier B. So which of these classifiers is better? The first way we might try and measure that is by counting how many errors the two classifiers make. Okay, so how many stars or peppers do they get wrong? So for classifier A, the error is going to be equal to 2. All right, so it gets all of the peppers correct and it gets 2 of the stars wrong. For classifier B, the error is going to be equal to 1, 2, 3, 4, 5. So B gets all of the stars correct and it gets 5 of the peppers wrong. So if we just consider which classifier has the lower error, we would say A is the better classifier. It has a lower error than B. It only made 2 mistakes. But is it really better? Well, maybe it doesn't look better from the picture. So another way of thinking about that might be to say, well, classifier A gets all of the peppers correct, but it only gets half of the stars correct. Whereas classifier B gets all of the stars correct, and it gets the vast majority of the peppers correct. So they both get one class right, but one of the two is much better in terms of the other class. So by that measure, we would select B as the better classifier. So maybe it's not entirely clear yet, but what maybe is obvious is that we need some better or different notions of what it means for a classifier to be good or bad. So long story short, the solution or the classifier which minimizes the number of errors may not necessarily be the best one. So let's consider some real-world examples where we may not want to select a classifier that minimizes the number of errors. So here's one. We have a data set which is highly imbalanced. Say I would like to train a predictor that estimates on Amazon which products would I purchase and which products would I not purchase. Okay, in this setting, there would be very, very few positive examples. So I purchase hardly any of the products across the entire catalog, and there'd be a huge number of negative examples. So naively, if we just had a classifier that predicted 0 everywhere, it would have very, very high accuracy. It would get a very small sample of the data wrong. But it would be a useless classifier. It would have no ability to estimate what kinds of products I would purchase. Really then, what we might like is some kind of error measure or some kind of classification scheme that would assign higher weight to those products which I did purchase. Okay, a second setting might look like this. Imagine you're scanning baggage at an airport and you're trying to look for dangerous items. What kind of classifier should I choose to do this? So the classifier decides, is there something dangerous, yes or no? And if yes, maybe it will get additional screening. So in this case, we have one type of mistake being very costly and one type of mistake being just a nuisance. So if I say there's a weapon when there isn't one, this results in some additional screening and it's a bit of a nuisance. Whereas if I say there isn't a weapon when there is one, that's a very dangerous situation. So one of those errors is cheap and one of those errors is costly. Maybe I'd like to define classification schemes or classification error measures that recognize that one of the two types of mistakes might be more important than the other. Okay, and a third setting might be when we're using a classification algorithm for ranking, which is something we'll introduce later on. So if I type some search result into Google and it gives me a ranked list of results, what I would really want is that there are some good results among the top few most highly ranked results. So what does that mean? I have some classifier that decides whether the result is relevant or not to a particular query. Maybe it assigns it some confidence. All I really care about is that some of the most confident instances contain relevant results. That might be my best error measure to use, which is a bit different from accuracy. Okay, so in order to do this, I'm going to have to introduce a few notions that are more fine-grained than just the number of errors a classifier makes. So let's try and do that. Well, we have data that is split into two groups. We have negative instances, in this case stars, and we have positive instances, in this case peppers. We have some classifier, or our decision boundary, that determines what mistakes we have made. So we can, for example, treat our mistakes on the positive part of the data different from the mistakes on the negative part of the data. So how do we do that? Well, the first notion we'll introduce is the number of true positives. That's saying what number of the positively labeled data points did we predict as positive? Okay, so we're saying things that are labeled as true that we also predicted as being true. Or it would be this set of data points here. They are on the positive side of our classifier, so we predicted they would be positive, and they also have a positive label. Okay, second notion is the same thing for negative data points, so true negatives. These are things that are labeled as false, and we also gave them a false prediction. So those would be negatively labeled data points that we correctly assigned a negative label. Okay, so those are the things we got right. What about the errors? So the false positives, those are going to be the things that we predicted would be positive, but actually should have been predicted negative because they have a negative label. All right, so those are going to be the things on the positive side of our decision boundary that actually have a negative label. So these points here. And finally, the false negatives, that's vice versa. We made a negative prediction, but they actually had a positive label. So that would be these 2 points here. Okay, so now we have those 4 notions: true positives, true negatives, and false negatives, which correspond to different combinations of the values of the label and the values of the prediction. So we can now redefine our commonly used error measures in terms of these 4 individual components. When we talk about the accuracy, what we're really saying is how many predictions did we get correct out of the total number of predictions. Okay, so that will just be what did we get correct? That's the true positives and the true negatives divided by everything. So true positives plus true negatives plus false positives plus false negatives. And similarly, the error rate is just counting everything we got wrong. So that's the false positives and the false negatives divided by the same thing. True positives plus true negatives plus false positives plus false negatives. Okay, and some related accuracy measures include the true positive rate. So that's saying, what is our accuracy if we just consider the true positives? So among those things which have a positive label, how many of them or what fraction of them did we correctly identify as being positives? So we're just saying, how many true positives did we identify out of all of the things that should have been labeled positive or should have been predicted positive given positive labels? So which things are labeled positive? That's our true positives plus our false negatives. And similarly, we can say, what is the accuracy on the negative part of our data? So that's the true negative rate. So of the things that are labeled negative, what fraction did we correctly identify by predicting that they should be negative? So that's our true negatives divided by everything labeled negative. In other words, the true negatives plus the false positives. Okay, and now here's one commonly used error measure, which maybe addresses the issue we introduced at the beginning of this lecture. So this is called the balanced error rate, which is the average of the false positive rate and the false negative rate. So that's saying, how well did we do on the negative part of the data? And that's normalized to how many negative instances there are. And how well did we do on the positive part of the data? And that's again normalized to how many positive instances there are. And then we can just average the two of those things. So what I really like about this error measure is that it's very hard to cheat. It's hard to get a good value of the balanced error rate with a naive or trivial classifier. So the only way to get a balanced error rate of 0 is, again, as usual, to have a perfect classifier, but any kind of random or naive classifier is always going to have a balanced error rate of 0. So if we predicted everything being positive, well, we'd identify all of the true positives, but none of the true negatives. Similarly, if we identified everything as being negative, we get all of the true negatives, but none of the true positives. Or if we just estimated all of our predictions completely at random, we'd again have like a true positive rate of a half and a true negative rate of a half. Okay, so all we've done in this lecture is introduce a few different or more fine-grained ways of evaluating classification algorithms besides just using the error or accuracy or the number of mistakes we made alone. And we described some different situations where different diagnostic techniques, including several we'll introduce later on in this course, might be useful. So on your own, I would suggest taking one of the previous classification examples we developed in previous lectures and try extending it to include different kinds of error criteria. So rather than just looking at the accuracy or the error, consider things like the true positive rate, the true negative rate, or the balanced error rate.